Namaskara. Welcome to the third lecture of Fourier transform. I am Professor P.R. Humpiholi, Head Department of Mathematics, Karnataka Law Society's Gokti Institute of Technology, Belgavi. We are learning some topics on Fourier transforms, third module, third semester engineering mathematics 18 Math 31. So, last lecture, uh, we have seen the definitions and one example. Quickly, I will show you the definition. So these were the definitions we learned. Definition of Fourier transforms. Any function f of x was transformed to a function of s merely by multiplying the given function f of x by a weight function integrating between minus to plus infinity dx. So to get the inverse Fourier transform, whatever the s function we get or f bar s, this function we multiply by here positive, here negative, multiply by 1 by 2 pi outside, both the integrations minus to plus infinity. Direct Fourier transform dx, x with respect to x we are integrating, inverse Fourier transform with respect to s we are integrating. For more definitions, instead of e raised to isx, if you multiply by sine and integrate between 0 to infinity, again if you are integrating with respect to x, s will come out, and whatever the s function comes out, Fourier, this suffix s denotes Fourier sine transform. Instead of sine, if you use cos, you will get Fourier cosine transform. From these s functions, if at all you want to revert back to f of x, then use these definitions as inverse Fourier sine transforms. Similarly, we have got inverse Fourier cosine transform. At present, we are focusing on Fourier sine and Fourier transform and inverse Fourier transforms. That is definitions number 1 and 2. So I am again repeating that these 6 definitions will govern or governing these Fourier transforms. So if you know these 6 definitions, you can find all the solutions to all the examples of Fourier transform. This was the last example we did. Quickly find the Fourier transform of f of x equal to 1 in the range mod x less than or equal to a, equal to 0 in the range mod x greater than a. So we used this definition of Fourier transform, broke this minus infinity to plus infinity according to this range. In between minus a to a it is 1 and remaining part it is 0. So only here 1 and remaining part 0. We integrated and ended with a function of s. So now we are going to have second example. So this is dear students, this is class 3 Fourier transforms. Let us continue with the examples. So example number 2. As I told in the last class, maximum, let me use this notepad to teach you so that along with me you can write. So let me write the example number 2. Some function of x, find Fourier transform. Many times I will be using the short form ft. Fourier transform, find Fourier transform of fx equal to, it has two parts, either x or 0. X, it is in this range mod x less than or equal to a. Outside range it is 0. So let us draw this small function. So let me take x-axis, let me take y-axis. So x-axis, y-axis, mod x less than or equal to a is equivalent to minus a less than or equal to x less than or equal to a, means between minus a to plus a, some minus a I'll mark here, between minus a to some plus a, if I have suppose between minus a to plus a, suppose this is minus a line and this is plus a line. So between minus a to plus a, y equal to x line, that is, this is the function, and outside the range it is 0. Outside the range it is 0. So if it comes like this from minus infinity to minus a, it breaks here and goes to x function. From here to here it is a x function. Here it is 0 and here it is 0. Again it breaks here. So outside means this is mod x less than or equal to a range. This is outside mod x. This is outside mod x function. So again, according to this, we are dividing this whole range into three parts: minus infinity to minus a to plus a, and a to infinity, considering Fourier transform definitions. So let us go on to the Fourier transform definitions. So can you recall? Fourier transform of any function f of x is given by integration 0 to minus to plus infinity to the function f of x. You have to multiply by what is known by weight function e raised to isx and integrate with respect to x. Now this range is divided into three parts: minus infinity to minus a to plus a, and a to infinity. A small homework to you: wherever a is there, you go on putting 1. What you will get, you see, that is the homework. So in minus infinity to minus a, the value is 0, plus minus a to plus a, the value of the function is x. So here I have to write x. So x into e raised to isx becomes the middle integration, and the last integration is again 0. See here, 0 in the range of minus infinity to minus a, that is this is 0. In the middle range minus a to plus a, it is x. This x is written here x and x here. In the last range a to infinity, I am going to write again 0. So only the middle integration remains. So let us simplify. Whatever it comes, we write it as a function of x. So this value becomes some function of s Fourier transform, and this is equal to only the middle integration x into e raised to isx dx. In the Fourier series classes, you have seen how to integrate these using general rule of integration by parts. But anyway, once again we shall do it. X into, I will not write this here, alternatively positive negative signs, plus here minus here. In small bracket I am differentiating this, x becomes 1. In this flower bracket, second part, polynomials you have to go on differentiating till they become constant, because next term should be 0. This one directly integrate. So this integration with respect to x means the remaining parts are constants. So only the x part you should consider as variable. Only the x part you should consider it as variable. So this becomes just like e raised to 2x dx, whose integration is e raised to 2x by 2. In this rough column I have explained you. Instead of 2 we have got is here. So I have to write is here. So integration of this becomes e raised to isx divided by is, just like 2x by 2. So here once again if you integrate, once again is will come out, because once again if you integrate, one more 2 will come down, 2 square it becomes. Similarly, once again if you integrate, it will be e raised to isx divided by is. Once again if you multiply here, I square s square. This everything you have to substitute between the range x equal to minus 2 plus a. But let me explain you the general rule of integration by parts how I did. One is differentiation function, one is integration function. Differentiation function start with that and differentiate here. Integration function start with integration. So this coefficient of is will come down for every integration. So e raised to isx by is. Once again is will come and multiply here. Is into is is I square into s square. So we have completed integration. Now there are usual type of simplifications for which you should get used to. So if you are getting familiar to, not getting bored once or twice, if you practice, minimum number of examples are there, which is a benefit of this Fourier transform chapter. Now here upper limit a, if I substitute upper limit a, upper limit is into upper limit a minus the lower limit, minus lower limit, here also I have to substitute minus a, and here also I have to substitute minus a, minus is a. This is I should not forget, whole divided by is. So upper limit minus lower limit for the first term is over. Now let us simplify this. This I square term, I square is minus 1. So let us recall this and put minus 1 here. And if you put minus 1 here also, you are going to get I square and minus 1 getting cancelled. Hence, let me write plus sign here. Once again, this minus sign and minus sign of I square, minus and minus become plus. So that when I substitute x equal to a, upper limit is into a minus the lower limit x equal to minus a e raised to minus is a divided by I square we have already consumed, divided by s square, so that upper limit minus lower limit is over. Now again we are going to use a similar factor. Last example we have used e raised to I theta plus e raised to minus I theta divided by 2 is cos function theta, and e raised to I theta minus e raised to minus I theta divided by 2 is sine function sine theta. So every example almost we are using this basic. So let us continue our f bar s. If I start adjusting to this a we can take out. If you take a out, e raised to I theta plus e raised to minus I theta should be adjusted for cosine function. So that this I and s are not useful, divided by 2 you should have. Let me see what I can write. A common, e raised to I s a, that is e raised to I theta minus of minus plus e raised to minus I s a, that is e raised to minus I theta, something like this. So divided by is, now I'll write here. What I need extra is divided by 2. So that let me adjust here by dividing by 2, so that I have brought to the shape of cos theta. This 2 is extra, so I'll multiply by 2 here. So this becomes cos of SA. So this part is adjusted. Similarly, this part you have to adjust. So this is this type of function, e raised to I theta minus e raised to minus I theta divided by 2i you need. So what all you have to do? You multiply by 2i, you multiply by 2i here. So let us do that. Multiply by 2i. Let me take this s square outside and multiply by 2i. This 2i what you have multiplied is extra. This 2i and this 2i what you have multiplied is extra. This I was telling. And remaining part, remaining part remains as it is, e raised to I s a minus e raised to minus I s a. So this bracket is something like cos of sa, sorry, sine of sa. Cos here sa, sine here sa. Quickly, if I write in terms of sine and cos, the structure looks like this. 2 times a upon is cos function, let me write instead of sa as, plus 2 times I by s square sine function as. So these brackets are cos and this bracket is sine. Now if at all I want to make it very similar, with this I, if I take it out, take it up. So 1 upon I, if I take up in the numerator, it becomes minus I. So remember this, because I square is minus 1. That's why 1 upon I is minus I. So I can bring it up and write minus I. And this s square, if at all I want to bring here also, multiply and divide by s square. So what all I am going to do in the next case, first let me write the structure as it is. 2a by s cos as, 2I by, because this step is only algebraic simplification to bring the answer in a compact form. So what extra I am doing is, this I you bring up, making it minus I. So multiply by one more s, means here it becomes s square, and here you compensate by s multiplication here. So s by s square remains 1 by s only. So now s square is common, 2I is common. 2I is common and this s square is common. So simplification becomes very simple, because first term is negative term, second term is positive term. Let me write second term, this term first and this term second. So what it looks like finally, Fourier transform of a given function, therefore, or this is f bar of s is, this is nothing but 2I upon s square common, or 2I is common. This term I will write sine as, second term is negative, 2I already taken, as cos as. This whole divided by s square you can write common. So to the given function of x, we have created a coded function of s. For the given time domain function of x, this is the frequency domain function of s. So quickly what we did, given any function of x, Fourier transform how to find? Given any function of x, sorry, 1 minute. See here, we are given this function. So first I drew the graph. Every time drawing graph may not be necessary. So when I drew the graph, so this part outside the range mod x greater than a, outside the range it is 0. This is mod x less than a, inside it is function x. Outside the range it is 0, outside the range it is 0. So now using this definition and Fourier transform definition, first you should be able to write Fourier transform definition. So what is the Fourier transform of f of x? Every example if you go on writing, it is nothing but integration minus to plus infinity. You have to multiply by e raised to I s x fx. Integration minus to plus infinity e raised to I s x fx dx. So that you break this into three parts. Minus infinity to minus a, minus infinity to minus a, minus a to plus a, where it is x here, 0 here, and a to infinity 0 here. So three parts broken. So only the middle part you are integrating by integration by parts. So differentiation function x, integration function e raised to I s x, differentiation function keep as it is, differentiate it becomes 1. Integration function just like e raised to 2x. I told with respect to x the remaining all behave as constant. So that e raised to 2x upon 2, just like that. Once again if you integrate, one more is will come down and multiply here is into is, that is e raised to, so differentiation, go on integrating this, second integration e raised to isx by I square s square. Then wherever x is there you are putting limit. Dear students, always don't forget, with respect to what you have integrated, with respect to that you have to put the limits. See, we have integrated with respect to x. We have integrated with respect to x. So you have to put limit wherever x is there. Wherever x is there. So that we did, x equal to a, x equal to a upper limit, minus x equal to minus a, x equal to minus a lower limit. Divide by s as it is. This minus has become plus because I square is minus 1 makes it plus. Upper limit x equal to a minus the lower limit x equal to minus a. So integration is over only to bring into compact form of cos and sine. Get familiar to these two. This should be on your tip of your tongues, so that you convert in terms of cos function, convert in terms of sine function, and you can bring into some compact form. So some standard examples are there like this, you should practice. Let me go to the example number 3. Some examples are little big, but you should have, like next example, you should have patience. So shall I start with example 3? Example number. So when you get used to this, afterwards I'll use some PDF and start explaining you with a little speed. If this is a very important, many times these type of examples are asked. If in the previous two examples, wherever a is there, you put 1 and make one more example. Here, if f of x has two definitions, like either it is 1 minus x square or 1 square minus x square, or it is 0. It is this value if it is in the range of mod x less than or equal to 1, and already you are used to this. What is mod x function? And mod x greater than 1. So now find Fourier transform of f of x. After finding this, hence evaluate or deduce. There are two examples of evaluation. First one is 0 to infinity. In the first class or in the previous class, I was telling such type of integrations were very difficult to find without the knowledge of Fourier transform. So that curiosity we are breaking here. So let us see what is the exact value of this. Really it is very nice to see how we are finding the value of this. So 0 to infinity, one more is very similar to this. We are multiplying by one more cos function, x cos x minus sin x divided by x cube. Oh god, such integration we are finding, divided by x cube, just like the previous case, into cos of x by 2. Such a big integration value very easily we can find using the Fourier transform. So what we have to do? First understand, find the Fourier transform of this. First you should write the definition and apply this range. After using, whenever there is a evaluation part, after finding the answer, we should go for inverse Fourier transform definition. So let us find the solution part of this. Solution to example 3. Given, of course not necessary to write here, but in the examination you are writing here, given function, first you write down f of x equal to 1 minus x square or 0 in the range mod x less than or equal to 1, mod x greater than 1. If this equal to sign here and there, need not worry much. Now first let us consider Fourier transform of, be along with me with little speed, let us go. Fourier transform of f of x is nothing but, already you are used to it, it is nothing but integration. And you know that this is the kernel of the function, weight function we are multiplying. We forcibly bring s so that output becomes s, and into f of x dx. So this is having again three ranges, minus infinity to minus 1, minus 1 to plus 1, 1 to infinity. Only in this range the value is 1 minus x square, and in the remaining range the values are 0. So let us break this into 1, 2, 3 parts. First part, second part, third part, and let us add all these parts, and the values are nothing but first part 0, second part, the value of f of x in this range 1 minus x square. So let us write 1 minus x square carefully into e raised to isx. Very important example, please concentrate. This part 1 to infinity 0. So again, just like last example, only the middle part you have to integrate. So what we did, we applied Fourier transform definition. So we applied the function definition, which is broken into three parts. So integration is broken into three parts, and first and last part 0, middle part is 1 minus x square. So if I integrate this by parts, f bar s equal to, this is differentiation part, integration part. So I'll write differentiation part in one bracket, integration part in one bracket. Alternatively, minus plus, differentiation part in one bracket, integration part in one bracket. Alternatively, minus plus, that is this minus, this plus, differentiation part, integration part. So what is differentiation part? Differentiation part is 1 minus x square. Go on differentiating this in small bracket, minus 2x. Care should be taken that don't go to simplify here only mentally. So go on keeping as it is, 1 minus x square minus 2x. And what is the differentiation of this? Yes, I heard what you told, minus 2. So differentiation function first we keep as it is, then afterwards go on differentiating till you get constant, because next terms will be zeros. Integration function you should go on differentiating with respect to x. Every time is will come down, e raised to is x divided by first time is, e raised to is x divided by one more is will come and becomes I square s square. Oh, one more integration. Can you guess what will be the denominator? One more into is. So what you have guessed is correct. I heard it. This is, again we have integrated with respect to x, means limits are for x, minus 1 to plus 1. So everywhere upper limit minus lower limit, upper limit minus lower limit, upper limit minus lower limit. So let us do it very, very carefully. So now can you see this, that first part is going to become 0. So can you see that first part, because when I substitute upper limit x equal to 1, when I substitute upper limit x equal to 1 here, 1 minus 1, 0, minus, when I substitute lower limit x equal to minus 1, so minus 1, 1 minus minus 1 square. So that again this becomes 1 minus 1, again it becomes 0. So first term becomes 0 actually. So let me write first term is 0. Then we will come to second term. Second term, you see minus of minus plus, but I square is there. So I square is minus 1, minus here, and this minus 1, 2, 3 minus signs make the whole term negative. And here x equal to 1, upper limit. Let me substitute 1 here, 2 as it is, x equal to 1, e raised to is into 1, upper limit over minus the lower limit. X equal to minus 1, x equal to minus 1. So denominator s square remains as it is. So this is e raised to I theta plus e raised to I theta divided by something, so that you will get cos function. So here minus 2. I cube value is I square into I square is minus 1, so I cube is minus I. So if I write this as minus I, minus and minus will get cancelled. First let me write this is plus function, I remains. So this part I have simplified. Now wherever x is there 1, upper limit minus lower limit, x equal to 1 minus the lower limit x equal to minus 1, whole divided by s cube. So wherever x is there, when I substituted, please see that after integrating with respect to x, putting limits, x will vanish. Basic fundamental is there should not be any x term here, otherwise big 0. Once again I am telling, after integrating with respect to x, x should not remain. So something different output will come, that is s output will come. So remains is to make it a compact form. Naturally, one will be cosine function, one will be sine function. Can you help me to write f bar s starts looking like this, minus 2 here. So you need e raised to I theta minus e raised to minus I theta. So I need divide by 2, which is not there, multiply by 2, and here. So already one 2 is there. So minus 2 is there already, and I'll multiply by one more 2. So 4 upon 2 remains 2 only. Multiply and divide by 2. So this s square I'll drag it outside. What I did, minus sign as it is. This is minus of minus plus e raised to I theta plus minus e raised to minus I theta. I wanted divide by 2, multiply here and here 4 by 2. Similarly here, whenever there is in between minus sign, you need a 2i term. I is already there. You need extra one more 2, multiply by 2 here, multiply by 2 here. If you multiply by 2, it becomes 4. So this s cube also I will drag out, and numerator let me keep as it is. So you are used to this now. Only thing is familiarity. Familiarity is the best strength. ರೂಢಿಯಲ್ಲಿ ಯಾವ ಶಕ್ತಿ ಇದೆಯೋ ಅದು ಎದರಲ್ಲಿಯೂ ಇಲ್ಲ. So you should get practice. So now to make it more homogeneous, 4 is already there. This s cube and this s square, how do you make it? Multiply and divide by s. So let me do that also. Minus 4 s by s cube. This bracket is cosine function, plus as it is this 4 by s cube. This bracket is sine function. So more interestingly, I can take 4 by s cube also common. So if I write that plus term first and negative term afterwards, what I'll get? Just wait. So what we wrote here, sine of s. I was here. So if I simplify this, 4 by s cube, if I take common, 4 by s cube, first term I will write sin s minus s cos s. So given function I have converted in terms of x function is converted in terms of s function. So this has a name s function. The first part is over. Once again you see what we did. Given some x function, see here, we converted this x function by using Fourier transform. To some s function. So now whatever is asked, the deduction part is asked. Can you see this deduction part? Now the whatever s function has come, it has come like this, sin s minus s cos s by s cube. So we are almost nearer to have the deduction part. Now we have found the Fourier transform of this as sin s minus s cos s by s cube. Almost like this. Now for deduction part, there are two functions here, we have to consider the reverse part. So consider inverse Fourier transform. Just wait. So considering inverse Fourier transform of this, yeah. So first we have found the Fourier transform of this. For both of these, we have to consider inverse Fourier transform. Let us consider inverse Fourier transform by the definition of inverse Fourier transform, that is Fourier inverse of this function. Naturally, we will get back f of x via this operation, as if you are putting something into a machine and output is f of x. Just like you put something in the machine, milk, sugar, everything, and you get coffee outside. Similarly, this you are putting in the Fourier. So let us do that. So if I do that to this function f bar s, to this function means this function, never forget that. So now we will be copy pasting that here in the integration into e raised to, here negative sign is important, e raised to, for reverse we will be putting negative sign, e raised to isx d, what you can guess, for reverse function always yes. So after integrating, whatever the output is there, that will be again back to f of x. So now if I substitute this value, which is minus to plus infinity. If I substitute the value of f bar s, which is here, so f bar s is here, and here. So drag it here. So what you will get, 2 pi, will drag it here, so that you are going to have 4 times this complete bracket sine s minus s cos s. Of course, you need little bit of concentration, but with that you can enjoy it, into e raised to minus isx as it is, ds equal to 2 pi into f of x, because I have dragged this 2 pi also this side. Now one more fundamental thing we shall use here. Many of the times you have used e raised to I theta in terms of cos and sine. So let me write this fundamental. E raised to I theta is cos plus I sine. If it is minus here, you will get minus here. See, here it is minus, instead of sx there is theta. So why not I should write this 4 will get cancelled and it becomes 2, and I can transfer here as pi by 2x minus to plus infinity, this bracket as it is, sine s cos divided by s cube, e raised to minus I theta is cos minus sine minus I sine. Instead of theta there is cos theta minus I sine theta. So ds equal to this 4, if you transfer that side it becomes pi by 2 into f of x. Once again 4 becomes 2 by 4 here, pi by 2 into f of x. Now once I will multiply by cos function here, and once I multiply here sine function, and separate two integrations. So when I separate these two integrations, so nice it looks now. Shall we separate? I am waiting for you to write. Once you multiply by cos here, that's all. Remaining all same, minus 2 plus infinity, bracket as it is, sine minus s cos whole divided by s cube. Once you multiply by cos function, ds minus I into one more integration, you multiply by sine here, which is sine s. To this whole thing you multiply by sine. sin s minus s cos s divided by s cube into sin sx ds. Everything will go to pi by 2 into f of x. Now if you see, this is even function, because when you substitute minus s minus s minus s minus s, from this minus s minus will come out, from this s minus will come out, so completely minus will come out in the numerator. From this s cube also minus will come out, becomes same thing as this function, and cos is even function, so this whole integrand becomes even function. So even function minus to plus becomes 2 times 0 to infinity. Whereas because of this is already even, we have tested here, and this is odd function, so both together this integrand whole becomes odd function. So this whole integrand is odd function between minus to plus, so becomes 0 odd function with respect to s. So this is actually one more proof that this part is 0. So now using this even odd function property, let me write first integration becomes 2 times 0 to infinity remaining as it is sin s minus s cos s whole divided by s cube into cosine function. Note that this x is here also, this is becoming 0, is pi by 2 into f of x. F of x is a real valued function, plus I'll write 0i, which is not necessary right now because already you have considered it as 0. So that this part, if you write real plus imaginary, that by time also you can see that it is 0. This part is not necessary. I'll transfer this 2 also this side. So when I write that 0 to infinity and I interchange these two terms, s cos s minus sin s, when I interchange these two terms, a minus sign will come out. That minus sign also I will transfer here. So minus sign transferred, one more 2 transferred. Oh, fine. This is very helpful to us. Now already I told that there is x here also and there is x here also. Choose proper x for proper function. Now for the, can you read your first one? First one you wanted to find the value of a integrand, something like this. I'll remind you, where this part is not there, cos 0. That is only this part you have to find the value. So for that you have to choose the value of x, that you never forget, because whatever it is, right hand side also, left hand side also is x. You cannot choose for s. So you have to choose for x only. If at all you want this to be 1, you should have cos 0 by choosing x equal to, yeah, that is right. So that f of 0 value is 1, that you can see by, what is the definition of f of x? Let me remind you. It is in the range minus 1 to plus 1. It is 0 is also there. In the range it is 1 minus x square. So when I choose x equal to 0, it falls in this range. X equal to 0, 1 minus 0 becomes 1. So f of 0 becomes 1. So f of 0 becomes 1. So when I write 0 to infinity, s cos s minus sin s divided by s cube, these s values will not change. Only this x equal to 0 becomes it 1. So that is 1 minus pi by 4. So that is after choosing what you got, minus pi by 4. This is exactly the first evaluation we wanted. So after finding Fourier transform, after taking inverse Fourier transform, two events, two steps: taking inverse Fourier transform, choosing proper x. For the first evaluation, you have to choose x equal to 0. Second part is here cos of x by 2 is there, but you are not asked this in terms of s. Now instead of s, you can write t here, t here, t here, t here. The value will not change. So that change s to x, 0 to infinity, x wherever s is there. If you go on writing x, I told yesterday, this is just like changing some clothes of a person. Person will not change. That structure will remain the same, answer will remain the same. So changing s to x, sin x divided by x cube, dx is minus pi by 4 is the first evaluation. For the second evaluation, I am choosing carefully x equal to half here. When I choose x equal to half here, x equal to half is also in the range of minus 1 to 1, somewhere here. So you have to put half here, f of half, 1 minus 1 by 2 square. So that also you have to write. So for the second one, you have to choose carefully x equal to half. Choose x equal to half in this star. So let me write this as star. This is our star equation. Choose x equal to half here. Cos s by 2 will get. Remaining will not change. Only this x pattern half here, x pattern half here. So let us write x equal to half. I am going to end up with minus to plus infinity sin s minus s cos s, or what we have written star here, only that part let me take. So s cos s minus sin s it is. So minus pi by 4 into f of x. So that let me write in the same fashion, which is s cos s one minute, s cos s minus sin s divided by s cube, cos of something divided by 2 with respect to s was minus pi by 4 into f of half, and that f of half was 1 minus x square. Here I have to write x equal to half. So that is 1 minus 1 by 2 square. 1 minus 1 by 4 is 3 by 4. Here I have to substitute 3 by 4. So when I do that, minus to plus infinity s cos s minus sin s divided by s cube into cos s by 2 ds is minus 3 by 4 into minus pi by 4 into 3 by 4 just now we found. The final answer becomes minus 3 pi by 16. Here also I change s to x and write the final answer as minus infinity to plus infinity so this is star value. Let me show you what was the star equation. Star equation is already it is 0 to infinity. Already it is 0 to infinity. So if I do that small correction, instead of minus to plus infinity, it is 0 to infinity in the previous step also, and here also. So this is 0 to infinity, 0 to infinity, changing s to x, we are going to get 0 to infinity x cos x minus sin x divided by x cube cos of x by 2 dx equal to minus 3 pi by 16. So we saw that using such a Fourier transform, we can find the value of such complicated integrations. Let me do the next example, that is example number 4, using this presentation, so that hope you can see this example number 3. So this you saw example 2, this also you saw. Let me go to example 4. If time permits, with the help of this, I'll repeat all these steps, but before I close, I would like to do this one more example. Please have patience. Find Fourier transform of this function and hence deduce this. So again minus 1 to 1 is there. So remaining part 0. So minus infinity to minus 1, and remaining part 0 to infinity to 1, it is 0. In minus 1 to 1, again there are two parts. In minus 1 to 1, see this is like this, minus infinity in this example, minus infinity to minus 1, sorry, minus infinity to minus 1, minus 1 to plus 1, and 1 to infinity. These parts have become 0 again, but in this again, minus 1 to 0, this is negative part, minus 1 to 0, and 0 to 1, negative part, and positive parts will be considered. So only that much I will tell today to you, and remaining proof in the next class. Till that you also think, minus 1 to 0 negative part, what happens? Value of the function is mod x, 1 minus mod x. 1 minus mod x is negative whenever there is minus sign, and mod x is positive x whenever there is plus sign. Only thing is, you try this function. Next class I'll repeat. So this is again integration function, and you go on integrating, you should get the value as this part. So till that, next time again we'll start with this example, example number 4, and maximum example will be covering by this presentation also. Till that, whatever you have done, please see that you practice and become familiar with Fourier transforms. Till that, bye. We shall meet in the next class. Bye.